Hello all. In this lecture, we want to talk about a topic that is famous in mathematics and also in physics, and it's called the rate of change. First of all, what is rate of change? Rate of change is nothing but a measure of how quickly one quantity changes with respect to another quantity. Now, when we say how quickly one quantity changes, that quantity could be the dependent variable, which is denoted by letter y. And in application questions, in fact, it can be any kind of quantity. It could be like displacement, it could be like volume or any other quantity with respect to another quantity. And this other quantity is usually the so-called independent variable or x. So a measure of how quickly one quantity, let's say the dependent variable y, changes with respect to another quantity, let's say independent variable, that is x. So that's what rate of change is. But there's two types of rate of change. One rate of change is called average rate of change, AROC. The other one is called instantaneous rate of change, IROC, the abbreviation. Now, what is average rate of change? Uh, I'm going to explain. I'm going to come up with some formulas as well. But average rate of change represents the rate of change over a specified interval. So you must have an interval. You must have 2 points, and you're finding the rate of change over that interval. Then that rate of change is average rate of change. And I'm going to explain what it geometrically means, of course. But in case of instantaneous rate of change, it represents the rate of change at a specific point. So we have only 1 point in case of instantaneous rate of change, but in case of average rate of change, we have 2 points. That's the difference. Now let's consider part of the graph of a function. I called it y equals f of x. It could be any kind of function. This is part of the graph of the function. And I considered 2 points on this graph, point A, point B. Obviously, these 2 points have x coordinates and y coordinates. So the x coordinate of point A is x sub 1, y coordinate is y sub 1, and the x coordinate of point B is x sub 2, and y sub 2 is the y coordinate of point B. Now, what we're going to do, we are going to connect these 2 points with a straight line. So we grab a ruler and we actually join these 2 points, and we draw a straight line that is passing through these 2 points, just like this. And this line that intersects the graph at 2 points has a special name. So let me draw this a little bit more straight. Okay, perhaps a little bit better. So this line that intersects the graph at 2 points, or sometimes more than 2 points, is called a secant line. Okay, so this is called secant line. It's a line that intersects the graph of a function at 2 points or more points. And the slope of this secant is actually rise over run, if you think about it. So this is the rise, and this is the run here, okay? And the ratio of rise over run is called the slope of the secant. And this slope of secant represents actually the average rate of change between these 2 points A and B. So if I want to come up with some sort of formula, I'm going to say average rate of change, AROC, okay, equals to the ratio of rise over run. So that is rise over run, which is actually the slope of this so-called secant line. So I'm going to call M, which stands for the slope, M sub secant. It means the slope of the secant line. And instead of the rise, I can just show the change in the y coordinates. So from y sub 1 to y sub 2, the difference is y sub 2 minus y sub 1. That is the amount of change in y. So I'm going to write down here change in y, and then divided by the run, which is actually change in x. So I can write x sub 2 minus x sub 1. This was the slope formula from junior high school grades. y2 minus y1 over x2 minus x1 is the formula for the slope of this secant line. And the denominator represents change in x. But in mathematics, whenever you talk about any kind of change in any quantity, we use a letter from Greek alphabet. It's called the capital delta. So when we write delta x, it means change in x. Delta y means change in y. Delta t could be change in time. Delta v could be change in volume. Delta d could be change in distance. So in any kind of quantity, when you want to mention the change between two status of 2 points, you show this with delta. So instead of writing change in y, I can use mathematical notation. I can say delta y, which means change in y. And that is actually y2 minus y1. And this is going to be delta x. And all of these fractions you see I'm putting down here are all equivalent to one another, and all of them represent the average rate of change between the 2 points A and B. And furthermore, instead of using the y notation, I can use the function notation. And I can say this is actually f at x2 minus f at x1 using the function notation divided by x2 minus x1. I can say that because y equals f of x is the equation of the function. Another way that this is written sometimes, instead of x sub 1, x sub 2, we are using letters a and b for the x coordinates of points a and b. So we end up with f at b minus f at a, okay, divided by b minus a. So that's another way of, expressing the same idea of slope of the secant, but with a different notation. And sometimes instead of using x1, x2, or a and b simply, we are using a, and then instead of the x coordinate of point b, we use a plus h. Now you're saying, what is h? H is called an increment, and that is exactly equal to delta x, okay? So let's say h is like 1 unit, and a is like 5. So we're saying 5 plus 1 unit will be 6 units. So we're talking about the interval between 5 and 6. So this can be written as f at a plus h minus f at a over changing x, right? Changing x is delta x, which is actually equal to that increment. We call it h. So I can just write simply h over there. So you see that there is so many different ways of actually showing this slope of secant. There's different notations, so on and so forth. So all of these fractions, they represent one thing, and that is the average rate of change of y with respect to x between the 2 points A and B. Now this y could represent, for example, the volume of a sphere, or it could represent the displacement of a car on a highway, or it could represent like population of a city, for example. It can represent any kind of quantity, and this x can represent, again, any other independent variable. For example, time is a famous one, okay? Time in years or time in seconds, something like that. So this was the average rate of change formula explained in like so many different formats. You saw this y2 minus y1 over x2 minus x1 in junior grade of high school. But these are other notations that can be used. And when you think about it, they all represent the same thing, average rate of change. And as I said, geometrically speaking, they represent the slope of the secant line. Okay, so this is average rate of change. But what about the instantaneous rate of change, or that so-called IROC? Well, here, this is what is happening. Point B starts moving along the curved path towards point A. So what happens is that point B, instead of being where it is, it may be a little bit to the left, okay? Or it can move along the curved path little by little to the left, just like that, okay? So that point B becomes closer and closer and closer to point A, all right? When this happens, you can use your imagination. When point B comes closer to point A, this secant line, the red line, starts rotating actually counterclockwise. So this line is going to rotate like this, and when point B becomes extremely close to point A, then we have a situation where the secant line is actually touching the curve at almost one single point instead of the former 2 points. So we end up with a line like this, okay, that touches the curve at only 1 point on condition that point B becomes extremely close to point A. And the name of this line that intersects the graph at only one single point is called a tangent line, okay? So this one is tangent line. It crosses the, like it touches the curve at one single point, but the other one, secant line, intersects the curve at 2 points. Tangent line and secant line, these are the names, okay? Now, if we find the slope of this tangent line, then that is called instantaneous rate of change of y with respect to x. And it represents the rate of change at a specific point, and that point is point A actually, and it has a special name, to tell you the truth. The name of the point A is called point of tangency. Point of tangency is what it's called. Now, if we want to exactly calculate this instantaneous rate of change or the slope of tangent, at that point we need advanced tools in mathematics. We need to know a little bit about calculus. But right now here, we do not want to exactly and precisely calculate the slope of the tangent line. What we want to do is actually estimate. We want to estimate the slope of the tangent line with pretty much good accuracy, of course. And then we're going to say, okay, that number we find would be the slope of tangent representing the instantaneous rate of change. But we don't exactly calculate that, but we just estimate that, we approximate that, okay? In calculus, just to give you, some information, we are saying that the limit of this fraction delta y over delta x, when delta x approaches 0, meaning it becomes very close to 0 and becomes very small, in other words, point B becomes very close to point A, we say this is actually equal to the slope of tangent, which in fact represents the IROC, instantaneous rate of change. And you may say, for example, limit of, for example, f at a plus h minus f at a, which we had before, okay, divided by h, when h, which is the same as delta x, actually approaches 0. So this limit is representing the slope of tangent or the instantaneous rate of change. In what other way can we write this? We can say, for example, limit of, if we select, for example, if we select this point A and this point X, okay, then we can say f at x sub 2 becomes f of x, and f at x sub 1 is f at a, if we use that notation, then divided by x minus a when x approaches a, all right? When h becomes 0, not becomes 0, becomes close to 0, then that is when x approaches a. So we can say x approaches a. These are the formulas that you will see in calculus course in future. But all of these are, end of the day, equivalent. And the idea of limit, we are going to talk about it extensively in the calculus course. But what it means that if x, our independent variable, becomes extremely close to a, then in that case, this whole fraction, if you evaluate that, it's going to become very close to slope of the tangent line. As I said, we don't want to calculate the limits here. We do want to exactly find what the slope of tangent is, but we want to approximate that. And in order to approximate that, there are different techniques that in the next lecture I'm going to explain. But briefly, I'll tell you what we do. We grab a point B that is very close to point A, and we sort of cheat, to tell you the truth. We actually find the average rate of change like before, but between 2 points that are extremely close to one another. And the answer that we get, we claim that it's a good estimation of the slope of tangent, basically. So we don't really find the limit, but instead we are finding the average rate of change between 2 points that are not far from one another, but on the contrary, they're very close to one another. And imagine if point B becomes close to point A, the secant line will become very, very close to the tangent line. So if you find the slope of that secant line, which is like very, very close to the tangent line, basically you can say that you have estimated the slope of the tangent line. So that's the trick we are using here. So we will never calculate instantaneous rate of change. In fact, we'll be calculating average rate of change. But with this minor difference, that the 2 points that we select will be very close points, points that are very close to one another. Okay, that's the trick that we will be using in estimating IROC. AROC, we are going to calculate that because that's not a big deal. We just have to find this fraction. This one we will be exactly calculating it, but this one we're going to be only estimating it, okay? And there are different techniques of estimation, and we will just talk about them in the future lectures. So I hope you understood what the rate of change is, and I hope you understood how many different types of rate of change we have, and I hope you understood how each one of them are geometrically representing how, like, instantaneous rate of change represents the slope of tangent line, average rate of change represents the slope of the secant line. And I hope you also understood how I wrote all these formulas for just one idea, one topic, which is average rate of change. Thank you for your attention.